Welcome back. In this video, we're going to talk about the vector equations for circles and ellipses in R2. Recall from a previous video that we had the scalar equation for a circle centered at the point h, k with radius r as x minus h squared plus y minus k squared equals r squared. And this underneath this was the Pythagorean theorem. Remember, we have something like a squared plus b squared equals c squared. And we thought about the circle as all points. Perhaps we call the circle C as a set. So it's actually a collection of ordered pairs, x, y. And these ordered pairs are equidistant from h and k, and the distance is r. So we think about the distance between h, k and x, y as equal to r. That's where this equation came from. This is set notation. And we simplified that distance by recognizing that to take the distance between these 2 points, we subtract and then square, and then we take the 2 norm of the distance squared, and that's r squared. As we talked about previously, we could also write this scalar equation where the right-hand side is 1. We did not really speak in detail about why would we want to do this. In this video, we'll see more of this. This is a setup for a generalization of a circle. Isn't that exciting? Which we call the equation for an ellipse. Yay! We'll see that in just a bit. As a quick reminder, let's actually look at an example of this equation in action. So in this case, we're going to find the equation for a circle centered at the origin with radius 5. Of course, the solution for this comes immediately from that formula. We know that our circle is given by, well, it would be x minus 0 squared divided by 5 squared plus y minus 0 squared divided by 5 squared equals 1. And another way to write this, of course, would be x squared divided by 5 squared plus y squared divided by 5 squared equals 1. And then if you were really excited about life and math and you wanted to map this back to your previous knowledge, you might say that this is x squared plus y squared equals 25, or 5 squared. The reason that I wanted to write it like this is I want to start prepping you to think about ellipses in this way. A circle is a very special ellipse. Let's go ahead and now graph this equation for the circle on an axis. Here, I might as well zoom out here so you can see this a little bit better. Okay. In this equation, we're going to do a bunch of different cases, and we're going to look at what this looks like using these cases. So let's start with the y equals 0 case. If we set y equals 0, or we go along the center point in y, this part of the equation goes away, and we're left with a single x squared divided by 5 squared equal 1. Well, we know by algebra that we can then solve for x squared, so this would be x squared equal 5 squared. And of course, this means that when I take the square root of both sides, so this is the square root of 5 squared. Square root of 5 squared is, of course, 5. And then I have so many students make this mistake. the square root of x squared is the absolute value of x, which means really we have 2 points here. We have x is equal to -5 or x is equal to +5 based on our algebra of absolute values. And we see what that means is when we go along the y equals 0 line, here it is, that there are 2 points equidistant from the center. One of the points is over here at +5, one of the points is over here at -5. Let's try again. Instead of starting at the y equals 0 line, let's start at the x equals 0 line, which is the vertical line through the origin or through the center. Let's go ahead and repeat that process algebraically. Here we go. If we assume x equal to 0, in our original equation we had x squared over 5 squared, which would become 0, and then this is y squared over 5 squared, and we set that equal to 1, and of course we immediately see that y squared was equal to 5 squared yields 2 solutions by repeating the math that we just did. It yields the negative solution or the positive solution, and that means along this line we have the +5 and the -5, and each of these is ordered pairs. Underneath this you have 0, -5 or 0, 5, and that's exactly what you see here. And what's fun about the circle is that we can actually fill in the gaps if we set x and y to be along any particular line. Yeah, let's actually do that. Let's assume that we look at the y equals x line, which implies that we can solve for either x or y in terms of each other. So here we would look at x squared divided by 5 squared, plus normally we would have a y squared, but since y is equal to x, we have x squared divided by 5 squared equal 1. Of course, we can bring the 5 over to the other side. So now we've got 2x squared equal 5 squared, which of course implies that x squared is equal to 5 squared divided by 2. And then we can solve for x by taking the square root of both sides. Here we go. This becomes the absolute value. The square root of x squared is the absolute value of x. And over here we have 5 on the bottom and square root of 2 on top. And you'll notice that that is exactly the, kind of hard to graph this in my mind. Sorry, got a headshot there. So here, this one's over here, and this one's over here. And I notice that's along the line y equals x. And then you can kind of interpolate to create the entire circle. Let's see how good my drawing skills are. When I was a young person, I used to take a lot of pride in my ability to draw. And then I got old. And I realized that Mathematica can do a way better job than I can ever do. So that was kind of a depressing thing. All right, so here's our circle, and it's the set of all points. If you looked at any point on this circle, we would say that this is x comma y. Here, when we look at the distance on this, we would call this r. And then if you look at what r is, we said here's x and here's y. Really, this is x minus h and y minus k, if you think about the center point at h comma k, because the distance between this and this would be x minus h. In this case, it's 0, 0, so it doesn't matter. When we look at this, there are kind of two different things that we can look at. The value of r, when we look at the value of r here, we notice that we can write r as the square root of x squared plus y squared. And then we also know that x and y, if you looked at these in terms of the angle theta with this original arc there, we would know that the cosine of theta was equal to adjacent over hypotenuse, which is of course x divided by r. And then the sine of theta is opposite over hypotenuse, which is y divided by r. And what's really interesting about this is that this actually gives a parametric equation for the x and y coordinates along the circle. So when I look at x, I can say that the x of theta is r times cosine of theta, and y is r times sine of theta. And then if you wanted to introduce the variable t for time, this would be a solution to a periodic differential equation, which you'll see later in your life. Instead of theta, you could think about this as a time variable. Anytime you go to a park and see a young person swinging, there is a cosine solution to a ODE, an ordinary differential equation, under their swing. I think about that every time I push my son around. Okay, and what this means is that when we look at a vector equation for a circle centered at 0, 0, of course, we have an x of t and a y of t, where these are the equations for x and y, where r is the radius of the circle and t tells you the angle that you're passing through. Let's go ahead and boot up Mathematica and see how this works in practice. Here we go. Here we are in Mathematica. We're going to do a parametric plot for a circle. Let's begin by defining our circle as having radius 5 to correlate with this example that we just did. We're going to use parametric plot as the operative command. Here I'm just going to comment my parametric plot command. When I begin to graph, I say to myself, the parametric plot, I do an open and close bracket. Here's a good coding tip for you. Anytime you open a bracket, immediately close it. This comes from hours spent debugging in my younger years. I remember I used to first open a bracket and then not close it until I was done writing code, but sometimes I would forget, and then I would basically be searching for hours for that stupid closed bracket. One way to avoid that is just the moment you open it, immediately close it. Remember that the equation for a circle came from the cosine of the parameter in the x-coordinate, and then r times the sine of the parameter in the y-coordinate. Cosines are x, sines are y. Notice that we did a capital for cosine and capital for sine because these are native Mathematica commands. They exist in the Mathematica kernel. And then we're going to determine the values of t. Let's do something kind of fun. Let's start with t goes from 0 to pi. To get that pi symbol, I hit the escape sign first. So there's one escape sign. I type in pi and I hit it again. I only want one of them. Okay, let's go ahead and graph this sucker. Notice I get a circle, a semicircle, and the reason that it's a semicircle is because of the choice of my parameter. I'm going to control the plot range on this so that Mathematica gives me the range that I want. So this is one of the options on parametric plot. Here I'm going to go ahead and say there's the x, and there's the y. I would like my x to go from -6 to 6, and my y to go from -6 to 6 also. Now I'm going to hit enter. Now I've evaluated it. I'd also like to control my ticks if that's possible. So here I'm going to go ahead and do ticks. I open. The first ticks that I want are going to be the set -6, -5, -4, -3, -2, -1, and then let's just leave it like that. So notice Mathematica is doubling up here. If I go now 1, 2, 3, 4, 5, 6, so Mathematica will hit all of those tick marks. There's a better way to do that command, and it was with the table command. So if you remember, if I typed in table, and then inside the table, I'm going to say, please produce all values of I. where my I values run from -6 to 6. Let's go ahead and do this. Do you see that I get the same set out there, but it's coded? So here I can just replace this list that I've just typed with the table command, and I can do 2 of those, one for the X, one for the Y, and now I get a really cool way to control my tick marks. Let's go ahead and make this circle an entire circle by letting the parameter go from 0 to 2 pi. Notice that I can control how much of this I want. So let's do like 3 divided by 2 pi. Pretty fun, right? And if I started at like, I don't know, 1/2 pi. Isn't that cool? It allows me to kind of control the parameters. In this case, for a full circle, I would probably want to go from 0 to 2 pi. Here's my full circle. And let's go ahead and graph a point on this. Remember that if we called the point P equal to perhaps open and close brackets for my list, we said that 5 divided by the square root, I think that's control, yep. So I just got that by controlling. Now we got 5 divided by the square root of 2. You can always get those commands from the basic math palette, which is up here. I like to do shortcut commands because I don't like to have to click on stuff. But here's the square root thing if you wanted to put it in. Okay, so now we have this point P, and we can show this point on our graph by just combining the parametric plot command with a graphics command. Perhaps I should do something. Let me just go ahead and finish this particular call. So graphics, I open and close brackets, I open and close the inside. I'm going to go ahead and control the point size. Generally, it seems like a point size that's pretty good is 0.02. And then we'll say point P. Okay, so there's my point P. Kind of cool, right? And that gives us a circle. In the next video, we'll talk about the generalization of a circle to an ellipse. I'll see you there.